Hey guys. So this is probably the last video for module 3, which is crazy because I filmed them all in like one day, but for you it's like a week or two. So let's get started. So hopefully you need at least like an hour to work on the practice test, and hopefully you've been given time in class to work on that or work on it at home. So yeah, if you haven't, then pause this video and go do that, because this is the answer keys. So I already have it done. I just thought it'd be easier if it was already written out, and then I could just kind of go through and explain it. So the first one is asking about, gives you a wavelength. This is violet light. You want to use a violet pencil or pen. Violet light has a wavelength of about 410 nanometers. So the first thing I did over here, all this is just a conversion, right? This is my conversion from nanometers to meters. Then to get the frequency, I pulled this equation, C equals wavelength times frequency, where C is the speed of light. Wavelength and frequency go together. This was in the very, sure, it's so creaky. This was in the very first set of notes that we did, this equation here, C equals wavelength times frequency. And I plugged that in, solved for the frequency, and got this number. Then it wants me to calculate the energy. So I pulled this equation from the next page of notes. I decided to go with energy equals H times frequency. Since I already just got the frequency, might as well use it. Copy pasted that in and found that the energy of the wave was 4.85 times 10 to the negative 19 joules. If this is the energy of one singular tiny photon, just one little light speck, the question is, how much energy would a dozen of the light specks have? And all you have to do is take your answer, multiply it by 12 to get this. And part D is just a reminder that kilo means 1,000. So if we're converting our answer from joules into kilojoules, we're going to take it, divide it by 1,000. And the only thing that's really changing here is that exponent. So that's number 1. If you're wondering, you can get more practice on this equation in homework 3.1. And you can get more practice on this one in homework 3.2 if you need it. So I'm going to leave this here in case you want to take a picture of or a screenshot of what's on the screen. Okay, the next one says, consider the Bohr model of hydrogen. Okay. So I drew it over here, and we're going to calculate the energy of an electron in the n equals 2 level and the n equals 3 level. It tells me later in part D that I'm actually going from ring 2 up to ring 3, and skipping ahead, that means I'm going to be absorbing energy, because electrons require an input of energy when moving up the rings and release energy when they fall. So I kind of just jumped and answered that question immediately. After that, I used this equation and this equation. Those are the exact same. I got this equation from homework number 3.4 on the back side. This 2.18 number was given to me. The 1 and the 1 here are just the fact that hydrogen has only 1 proton in it. And the excuse me, the denominator squared is coming from the 2 here and the 3 there. So I plugged both of those into my calculator and I got 5.45 times 10 to the negative 19. That's the energy level of ring 2. And the ring 3 was 2.42 times 10 to the negative 19. At this point, do not worry about the signs. Yes, that says negative. Yes, that says negative. Who cares? Doesn't matter. Just pretend that they're not there and subtract. 5.45 times 10 to the negative 19 minus 2.42 times 10 to the negative 19. So basically 5 minus 2 is 3. And I put positive here. This is where it does matter. That positive sign is meaning that we are absorbing energy to go up. If it was traveling downward, I'd say put a negative there, but it's not. Okay. So this is how much energy it costs to move up that same area. It would be the same amount of energy to go down, but that's why we need the plus or minus in the front to tell us which direction the electron is going. Then we're going to use our answer from part C. It says, if a photon of light had this energy from part C, that's what we're going to plug in for the energy, then what would its wavelength be? This equation is the alternate equation from the notebook. It doesn't involve frequency. It's the one that involves wavelength. Energy equals hc over wavelength. So I plug that in. Here's my answer from part C. H C divided by wavelength. I solved for the wavelength. And the last part is just to do that conversion from meters into nanometers. You can use the 3-digit trick, or you can go the long way and say 6.58 times 10 to the negative 7 times 10 to the 9th power, because it's a nanometer, gives you 658. So here is the screenshot for number 2, if you would like. Okay, the next one, number 3, is this whole problem. You can get extra practice if you go back and do homework 3.3. A photon hits a metal plate and is ejected from the metal surface. Sorry, a photon hits a metal plate and an electron is ejected from the metal surface. If the wavelength of the original photon had a wavelength of 250 nanometers, which I just immediately converted, and the ejected electron had a velocity of this problem is kind of different because normally you're finding the velocity, but it actually is giving you the velocity, and you're going to have to work backwards and find what the work function is. Don't overthink it. It's the same problem that we've done before. Just think to yourself, okay, if light's coming in and it's got 100 joules and I don't know the work function, but it's leaving with, I don't know, 10 joules of energy, then you can figure out that 90 joules was how much the impact cost. We're doing the same exact thing. We just have to figure out what are the two numbers up here so we can subtract. To get the first number, what I did was I used this equation to calculate the energy of the light coming in. This is the photon energy. I then use this other equation from, you get it from homework 3.3. I used this equation to calculate this number over here. 9.1 times 10 to the negative 31. That is always the mass of an electron in kilograms. And I got this number from the problem. Mass times velocity squared. So this was the energy left over after the impact. In order to get my final answer here, like what is the work function? Just like before, if this was 100 and this was 10, I would subtract to get 90. I took the two values, subtracted to get this. So there's number 3. You can take a picture if you need that one. All right, next one, number 4 gives us the barcode spectra for neon. And neon's got so many, look at it. Like neon only has 10 electrons, but like, holy cow, that is so many stripes. It says that our brightest line, the one that like just shines the most, is at 865. But we've got other lines at 838, 878. I wrote that one twice, whoopsie daisy, and 1885. So the first question says, which of the ones listed above are the most energetic? So the most energetic waves are going to be the ones with the highest frequency, which means the shortest wavelength. So I just went back and looked at the numbers and went 838, that's the shortest wavelength that was listed. So that one. Maybe there were shorter ones that weren't listed, but from the ones that were listed, 838 was the most energetic because it's the shortest wavelength. In homework 3.4, there was a little chart that you could use to figure out that 800 nanometers is infrared. But what I basically just remember is that visible light ranges from about 400 to 700. And if you go past 400, like if you get into 300, then on that side, you're going into ultraviolet. And if you get a little bit past 700, you're into infrared. So I thought, 838, that's not like too far past 700. I'm just going to go with infrared, but you could use the table if you needed to double check. It says that 865 was the brightest stripe. So I brought that number down, converted it into meters, and used C equals wavelength times frequency in order to get my frequency. Once I had that frequency, I plugged it in here. Energy equals H times frequency, where H and C are constants, so you should never be asking what those are. C is always the speed of light, 2.998 times 10 to the 8. And H is Planck's constant, which is 6.626 times 10 to the 34. And here's that one if you would like a screenshot. The next one down here, I didn't finish. It's mostly conceptual. So number 5, the world around us can be categorized into energy such as waves or particles such as matter. Thomas Young proved that light has wave properties using the double slit experiment, which involved ... And this is where you would want to make sure that you study and that you understand how that experiment worked. Additionally, Albert Einstein was the other scientist that proved that light also has particle properties in addition to wave properties using the photoelectric effect experiment. So make sure that you understand what those experiments were. And if you need a refresher, you can rewatch those videos that I recorded, or you can also read the notes that we have called Light as a Particle and Light as a Wave. The next one says we're going to compare a radio wave and an X-ray. So I drew out a radio wave, really, really long, see, and then an X-ray is like really, really short wavelength. So first question just says which has a higher, that means longer wavelength. That would be my radio wave. But the X-ray would have higher energy because when you've got that big, long wavelength, you're not very frequent. You do not have very much energy. So the X-ray is going to be much higher energy than the radio wave. Which wave or waves could a human see with their eyes? The answer is neither. We would only be able to see what's called the visible region for a reason. And this is one that a lot of students miss. Pat yourself on the back if you got this right. Which wave is traveling faster? Explain. Both are traveling at the same speed. They're both traveling at the speed of light. One is just more wiggly than the other. So this is like when a mom and her little kid are walking at the store. They're both moving at the same speed, but the mom's steps are like 1, 2, 3, and then the poor little kid is like cha 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 cha, taking like a bunch of little steps in between. So the mom is like the radio wave, like step 1, step 2, and the little kid is like step 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 step, but they're still walking at the same speed, holding hands. That's kind of what's going on there. Wavelength and frequency are inversely related. The longer that your wave is, the less frequently it's occurring. Let me say that one more time. The longer that your wave is, the less frequently it's occurring. So inverse. The longer the wave is, the less energy you have. The higher frequency you have, the higher energy you have. So frequency and energy are direct, while these other ones here are inverse. And last but not least, here is a bright line emission spectra. All you've got to do is figure out what elements are present in the mixture. And I saw that looked like it matched. And these 4 lines look like they match. And this one, I couldn't see any evidence that it had made it into the mixture. So my final answer was elements D and Z were present in the mixture. So that's it for Unit 3. Your test will be very, very similar to the practice test. It will just, changes that you can anticipate might include, instead of number 1 saying violet light has a wavelength of 410, maybe I switch it up and you get green light that has a wavelength of whatever, or maybe you get red light, and that's going to change all the numbers, but the process would still be the same, right? Same thing, like number 2, we had a jump from 2 to 3. Maybe I'd flip it and you'd be going from 3 to 2, or maybe 4 to 2, or maybe 5 to 2. And you just have to change the step, the difference. So that's more what the test is actually going to be like. It's, I would say, very similar. Just make sure you understand, like, go through the test one more time and ask yourself, like, how could Miss Oliver copy and paste this over? And then, like, what could be changed? And that's your best bet for figuring out what you're going to get asked on the test. So best of luck to you guys. Please reach out as always if you have questions. I'm more than happy to send you, like, if you need extra answer keys, or if you want to meet over Zoom, that's totally fine. So email me, and good luck. Bye.